The following video will demonstrate how to use response surface approximated optimization with user-defined points as a starting strategy in VisualDOC. In this video, I will be using design of experiments component to create design points. Design of experiments component is explained in the previous video in detail. Link for the video is provided in the description section. The idea of response surface approximated optimization is to create explicit approximation functions to the responses and use these when performing optimization. Once approximations have been constructed, they can be used as a function evaluators, replacing the underlying computationally expensive analysis tools. It is very important to note that you should have analysis results for minimum number of design points in order to construct polynomial. The response surface approximated optimization methods can be used when number of design variables are comparatively small and cost of analyzing a single design is high. Let's start with an example. I will be solving stepped rectangular cantilever beam problem. A cantilever beam with 3 equal length segments is used. The total length of the beam is 500 centimeters. The beam is loaded with a vertical force of 50,000 newtons at the tip. The design variables are width and height of each segment. Responses includes volume of the beam, displacement at the tip, and the maximum stress in each segment of the beam. Here, objective is to minimize the volume of the beam. It is subjected to constraints. Displacement at the tip of the beam should be less than or equal to 2 centimeters. For maximum stress in each segment, lower bound is minus 20,000 and upper bound is plus 20,000 Newton per centimeter square. Constraints on design variables. For width of each segment, lower bound is 1 centimeter and upper bound is 5 centimeters. For height of each segment, lower bound is 40 centimeters and upper bound is 60 centimeters. This is a simple example for demonstration. VisualDOC has a capability to solve extremely complex optimization problems. Now, first we will create design points which can be used as initial set of points for starting strategy. Starting strategy controls initial distribution of points. The first iteration of a response surface approximated optimization component creates initial set of points using specified starting strategy. Now let's open VisualDOC. Now click on File button from the main menu bar and select New Project. Select the folder where you want to save the project. Click on New Project Database button. Now add a Design of Experiments component. Next, select the executable wrapper component and add it inside Design of Experiments component. Now add a stop block. Now click on Flowchart Components in the Model Tree panel and click on Auto Connect All Models icon to connect all the components. Next, click on Automatically Rearrange All Models icon and select Yes. Now I will rename the executable wrapper component. Right-click on executable wrapper component, select Rename Component. Click OK. Now next step is to set up the executable wrapper component. Go to Component Editor tab. Select Beam Analysis from Model Tree panel. Now enter the data in the middle panel. For responses V, D, S1, S2 and S3, select Output from drop-down list in Input-Output column. Initial value for W1, W2 and W3 is 2.5 and for H1, H2 and H3 is 50. When coupling analysis with optimization, it is necessary to have an input data file and an output data file that correspond to the analysis program. The input data is utilized to override values that correspond to the design variables. The output data is utilized to extract output responses. During optimization, the input file is modified by VisualDOC automatically and output file by analysis program. In the panel on the right, under Run Location section, make sure that Analysis Runs Locally radio button is selected. Under Analysis Working Directory, make sure that Use the Model Directory option is selected for directory part type. For local analysis program definition, make sure that relative to analysis working directory option is selected for file path type. For file path, click on file icon and select your analysis file. Analysis file is an executable file to calculate responses. For input file definition, make sure that relative to analysis working directory option is selected for file path type. Now click on file icon and select input file. Under output file definition, for file path type, select relative to analysis working directory. For file path, click on file icon and select output file. Under analysis program definition, input file definition and output file definition, I have selected relative to analysis working directory option as a file path type, as I have saved the input, output and analysis file in the same location as that of VisualDOC model. Now push the test button to ensure the connection between VisualDOC and analysis program. After successful execution, you will be able to see the computed values in the initial value column, and you will get a message under Standard Messages tab. Next step is to create data transfer. Go to Data Linker tab. Select Design of Experiments in the Model Tree panel. Select Design of Experiments in the middle panel. Make sure that Auto Link checkbox is selected. Now click on Automatically Add Data to Selected Model icon. This will create the data needed for the design of experiments and add corresponding links for the data transfer. Now we will set up the Design of Experiments component. Go to Component Editor tab. Select Design of Experiments from Model Tree panel. For variables W1, W2 and W3, lower bound is 1 and upper bound is 5. For variables H1, H2 and H3, lower bound is 40 and upper bound is 60. From the panel on the right, for DOE action, select Create DOE points with responses. This will create a set of data points and perform an analysis for each point to generate the response data. And select 2 raised to 6 minus 1 fractional factorial from the options drop-down list box. Total number of design points generated will be 45. Now click on File icon and select Save as a new task. VisualDOC will save the current model as a new task in the same database. Now click on Run icon. Now, next step is to create workflow for response surface approximated optimization. Go to Workflow tab. Insert response surface approximated optimization component. Now right-click on Beam Analysis component and select Cut. Then right-click inside Response Surface component and select Paste. This would make Beam Analysis component as a subflow for the Response Surface component. Now right-click on DOE component and select Delete. Now select Stop Block from Model Tree panel and click on Move down the selected node icon. Now click on Flowchart Components in the Model Tree panel and select Auto Connect All Models icon. Now click on Automatically Rearrange All Models icon. Select Yes. Next step is to create data transfer for Response Surface component. Go to Data Linker tab. Select Response Surface from the Model Tree panel. Select Response Surface in the middle panel. Make sure that Auto Link checkbox is selected. Now click on Automatically Add Data to Selected Model icon. This will create the necessary data for Response Surface component. Now we will set up the Response Surface component. Go to Component Editor tab. Select Response Surface in the Model Tree panel. For variables W1, W2 and W3, lower bound is 1 and upper bound is 5. For variables H1, H2 and H3, lower bound is 40 and upper bound is 60. For volume V, select the checkbox in Objective column and deselect the checkbox in the Constraint column. Make sure that Minimize option is selected in the goal column. For constraint D, upper bound is 2. For maximum stress in each segment, lower bound is minus 20,000 and upper bound is plus 20,000. From the panel on the right, select Forward Stepwise Regression for the model order. For starting strategy, select User Define Radio button. Now push the Create or Edit Design Points table. Now click on Import from Database button. Click on Different Task button. Now select the task which we have saved in the earlier part. Click on Open the selected task. Click on Expand Complete Hierarchy icon. Select W1 and push the green arrow to extract data. Repeat the steps for all variables and responses. Now push Next button. Select the existing invocations and click on blue arrow. Now push the Finish button and select OK. Now I will create two simulation monitors to monitor the best objective and the worst constraint violation. Go to Simulation Monitors tab. Add two optimization history monitors. Click on Expand Hierarchy icon below the Flowchart Components panel as well as the List of Monitors panel. Drag the best objective under Simulation Parameters and drop it on the x1 axis of the first monitor. Similarly, drag the worst constraint under Simulation Parameters and drop it on the x1 axis of the second monitor. To activate all defined monitors, click on Enable All Monitors icon. Now, click on Validate icon. Our complete model is valid. Now click on Run icon. To view the defined monitors, go to View Monitors tab in the message area. For both optimization history monitors, x-axis represents number of iterations. Total number of iterations are 31. For first optimization history monitor, y-axis represents best objective value for each iteration. For second optimization history monitor, y-axis represents worst constraint value for each iteration. For 0th iteration, volume was 75,000 cubic centimeters. After 31 iterations, it has been reduced to 51,959 cubic centimeters, satisfying all constraints. To view the optimum results, go to Component Editor tab. The table displayed in the middle panel has the optimum values in the optimum column. The total reduction in volume is approximately 31%. This completes the demo. I hope it has helped you to get familiar with response surface approximated optimization in VisualDOC. If you would like to learn more, I invite you to check other videos about VisualDOC. For additional information, please visit our website at www.vrand.com or email us at visualdoc.support@vrand.com. Thanks for watching.